So thank you for the invitation. And my name is Hadar Steinberg. I'm from the Hebrew University, so I'm the local guy, so I don't have to tell you about Jerusalem because you are in Jerusalem. The campus is 10 minutes away. I understand that you were taken to see the Dead Sea Scrolls. So just from the, you're taking tomorrow. So if you're there, if you look over to the next hill, that's my lab. That's there. So it's the hill next door to the museum is the Hebrew University. So I'll be talking about devices consisting of two-dimensional superconductors from transition metal dichalcogenides. So we heard about Josephson devices with spin orbit yesterday from Ora, and we heard about transition metal dichalcogenides today, and heard about vortices earlier today too. So everything will be in this talk. So I'll start the talk by telling you about, oh, this thing is not working, okay. An autobiographical fact that there are three things I wanted to achieve as a scientist. The first thing was to publish a paper with my wife. The second thing was to begin a paper with a text ever since the ancient Greeks. And the third thing was to make a reference to Tolkien. Now, my wife is a biologist, so I can't publish a paper with my wife. I don't work in magnetism, so I can't refer to the ancient Greeks. But I'll show you today that I can make a reference to Tolkien. So that'll be in the second part of the talk. So this work was done in my lab right here at the Hebrew University. These are the generations of students who actually did the real work with experimental collaboration with Jonathan and Aharony, who's a scanning squid expert, and lots of theory done recently by Yaakov Linder and his students and with Anna Kesselman from the Technion. So we heard about transitional metal dichalcogenides as optical media, but now we'll talk about the same materials as superconductors. If you look at materials such as MOS2 or tungsten diselenide, the same structure is shared by niobium diselenide and tantalum sulfide. It's a transition metal with chalcogens on both sides. And in the H structure, we have a structure of orbitals that basically allows us to have a certain kind of symmetries which induce a very, very strong spin orbit effect. So the spin orbit effect that gives these effects of polarization that we heard about earlier today has a very special role when we talk about these materials as superconductors. Niobium diselenide and tantalum disulfides are basically like MOS2 but doped. They're very strongly p-type doped. They're superconduct with transition temperatures in the bulk of about 7 Kelvin for niobium diselenide. And the property of spin orbit is such that the effective crystal field times the momentum, the propagation direction, which has to be in the plane, imposes a spin orbit effective field which is out of the plane. That means that you have an extremely strong field which locks the spin of these electrons out of the plane. What this field does, it stabilizes Cooper pairs. This means that if we look at this material, and one of the great breakthroughs of the two-dimensional device fabrication about last decade was the ability to single out single layers of these materials and study transport. And once you have a two-dimensional system, then all the pairing effects coming from the bulk disappear. Basically, if you try to impose an in-plane magnetic field, there is no longer a Meissner current that's going to destroy superconductivity. So basically, the only thing that's going to stabilize superconductivity is what happens to the spin. Now, because the spins are locked, that means superconductivity is protected, and there's this very important paper by the group of Kinfei Mack that shows you can actually have superconductivity up to 30 Tesla in the plane. And studies on niobium diselenide show that if you go from bulk to 4, 3, 2, 1 layer, the TC goes down to about 3 Kelvin, but you still have superconductivity. Interestingly, tantalum sulfide, you have an opposite effect. You go from bulk 4, 5, 4, 3, 2, 1, you meet again at 3 Kelvin, and you have a monolayer which still remains superconducting. Now, what we are interested is taking these devices and carrying out a number of several types of experiments. This sort of bread and butter experiment from my lab are tunneling devices, and I'm going to talk as sort of a preliminary about these tunneling devices. We build devices where there's a defect inside the tunnel barrier, and the defect serves as a quantum dot, which can serve as an SCT or a spectrometer. And I'm pretty sure I'm not going to have time to reach that. The focus of the talk will be these two subjects. One are Josephson devices consisting of very thin niobium diselenide and graphene, which are entirely planar. and a new type of device which we developed together with my colleague Jonathan Aharony, which is a vortex management device allowing us to shuttle superconducting vortices or precursor vortices between various sites on a sample. So let's start with tunneling devices. Basically, everything we do is based on the architecture of exfoliating and stacking. So we exfoliate a superconductor. That happens to be tantalum sulfide, very, very thin tantalum sulfide. We transfer a thin semiconductor on top, which in this case happens to be moly disulfide, and we write electrodes on top. So what we have is the structure of a superconductor. This is the tunnel barrier, and you can see that the tunnel barrier engages very, very nicely at the atomic scale in this cross-section TEM with the superconductor, and the electrons tunnel through the tunnel barrier into the superconductor. And we've been using this technique over the years to study a number of systems. We studied niobium diselenide, which has a two-gap superconducting structure, and we've been working for a while trying to figure out this two-gap structure. We've been studying H-tantalum sulfide, and this is a monolayer H-tantalum sulfide. This is the only tunneling data that exists on monolayer H-tantalum sulfide on an insulating substrate. And we're going to submit this data soon. And we also studied the material iron telluride selenide, which is suspected as a topological superconductor. You can see here that it retains a gap at very high out-of-plane fields, which probably has to do with the fact that it has very, very sparse vortex states. Now, what you really care about in these materials is what happens at high magnetic fields, because high in-plane magnetic fields, they're supposed to remain superconductors, but then there's the question of what does the magnetic field do to them. So one thing we can show, for example, with this tantalum sulfide, if you look at it bulk material, you crank up in-plane magnetic field, you destroy superconductivity. You can see that here. As you go to thinner and thinner layers, you can see the superconductivity becomes more stable, and this is data taken from in-plane 0 to in-plane 8 Tesla. So this is an 8 Tesla in-plane. The gap stays unchanged. That's actually very, 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 very important, because it gives us, it's both an interesting experimental system, but it's also an experimental tool, because it will allow us to do several things that can't be done with other materials. That's going to be the core of this talk.
What is TC?
And the TC is a 3 Kelvin. 3 Kelvin, yeah. So the TC we measure in tunneling agrees perfectly with TC that we measure which is measured by others in transport.
Why do you have a larger gap compared to bulk?
That's a very, very good question, and nobody knows the answer, but it's very consistent between the gap and the TC. TC and the gap go linearly with the perfect 1.76 ratio, as BCS theory predicts. The leading theory claims that it has to do with the charge density wave order, which seems to compete or suppress superconductivity in the bulk and not do this as effectively in the monolayer. But that's somebody else's theory, not mine. Yeah. So what we were able to do, for example, is measure the HC2 and see that HC2 increases very, very strongly in the monolayer samples, and that it's proportional to delta square, which means that it looks like a clean ballistic superconductor. But that's enough about tantalum sulfide. In a very challenging set of measurements, we took a 2-layer niobium selenide tunneling device, went to Grenoble and measured it at very high magnetic fields, up to 30 Tesla, and you can see that the gap survives. And there's been piles of theory led mostly by my colleague Maxime Chodas and by Julia Meyer and Manuel Huza, which basically address this problem in the following way. If you look at the spins which are up and down, what magnetic field does, it tilts them. And according to theory, there's supposed to be some kind of a triplet order. And it took about 2-3 years for the theorists to argue that this dip, the survival of this dip, is consistent with the triplet order. Now all we need is to convince some referees in the editor, but that's a different problem. Physically, this seems to be a very, very stable gap surviving up to very, very high fields. So that that could have been a whole talk, but that's the preliminary part of the talk, because now I'll tell you what I can do if I have a superconductor that survives very high in-plane field, and I want to build Josephson devices that survive very, very high fields. And that's going to be this first part of this talk. And the background is the following thing. We want to use a niobium diselenide lead, source and drain, and a graphene weak link. Now, graphene weak links have been studied initially by the Delft group. It was Hirsch, Herrero, Morpurgo, and van der Siepen. This seminal paper showing that graphene these are aluminum leaded, graphene can support Josephson effect superconductivity. There are many, many papers using very, very similar methodology since then. Your friends in Pohang University, Postek, built this device where you have an NBSC2, graphene NBSC2 vertical structure. That's a paper that's been cited quite significantly. So you have vertical tunneling through graphene here. And in a subsequent study, the same group used correct niobium diselenide to contact a graphene weak link. We did the same, not knowing that they were doing the same. So it's basically doing the same thing. And your friends published before me. What they didn't do is apply an in-plane magnetic field, which is what we do. So, what happens if you take such two planar Josephson junctions and apply an in-plane magnetic field? This is seen to be a real drive of several major groups. You have Nadia Mason taking a piece of bismuth selenide, building basically a very simple Josephson junction, applying an in-plane field. And also the group of Amelia Jacobi. This is data with niobium leads. This is the same thing with aluminum leads. What's interesting here is the following thing. First thing is that what happens in in-plane field, and in the next few slides I'm going to argue that momentum becomes really important and spin orbit becomes really important. And the second is how poorly these devices survive. And the reason they survive poorly are twofold. One is that the 2D is not really 2D, because it has some kind of finite thickness. And two is that the superconductor is sputtered or evaporated aluminum or niobium. There's a certain limit to how well these materials can survive at high in-plane field. Even if they survive, remain superconductors, how well do they survive? So if you want to have the best superconductor to survive with completely indifferent to very high field, you go to niobium selenide. Okay, so our motivation is to build a structure which looks like that. There's niobium selenide, graphene niobium selenide, and we want to ask several questions. One is, how far will it survive? Will we have a Josephson effect? How stable will it be towards high plane field? What would limit this effect? And the second question is, in long term, can we see hints of triplet, or can we learn something interesting about the niobium selenide by doing that? And the interesting thing about these devices, they are tunable Josephson devices which contain no evaporated parts, at least not in the actual Josephson device. We need to put leads somewhere. The leads are not evaporated, they're van der Waals. And there is no oxide, because there'll be hexagonal boron nitride all around. So there's very clean, very stable materials all around. And I'm comparing to this study also from Delft, which took a graphene Josephson device with moly-uranium electrodes and tried to operate it as part of a transmon at in-plane field, reaching about 1 Tesla. So this architecture can't cross 1 or 2 Tesla. It's just simply the superconductors don't survive. So you'll see in a moment how far we can reach with the Josephson device. So another motivation to build these devices is that there's a growing body of literature telling you that spin orbit and in-plane field would give you topological devices. Majoranas at the edges. This is work by Adi Stern and collaborators in Weizmann, and that using this architecture you can actually map how does the momentum and spin orbit, how do momentum and spin orbit couple to each other. So this is how we build the device. We take a piece of niobium selenide and look for a very, very narrow crack. And these cracks are 150 to 300 nanometers wide. We transfer them on top of graphene, and then early devices were on silicon, later devices were on HBM. That you'll see the difference in the quality. So you have the path of the supercurrent is from the niobium diselenide into the graphene, through the graphene back to the niobium selenide. You put 2 electrodes here, 2 electrodes here, you have your 4-probe device. And you apply a current, measure the voltage, you see your nice, well-behaved Josephson device with 4 microamp critical current. You apply the gate, you see the supercurrent going down and then up as superconducting graphene device should behave. Then what happens if you try to apply magnetic fields out of plane and in the plane? Then you run into a problem. The problem is that there is no such thing as in-plane magnetic field. Well, you like to draw the field as a vector, but nobody guarantees that these lines are parallel, and nobody guarantees that they're parallel to the center of the magnet, and nobody guarantees that your sample is straight. So what are we going to do is you use a 2-axis vector magnet start cranking up the in-plane field, but compensate with an out-of-plane field. And I call this walking along the knife, because if you go too far from zero field on the junction, you get too much flux inside the junction. You're dead, you have to thermal cycle the device. So we've been thermal cycling many, many, many times, kind of falling off the knife edge. And this is what the data looks like. You scan a Fraunhofer scan at zero field. Nice looking Fraunhofer. You see lobes. You see a central lobe at zero. You start cranking up the in-plane field. And disregard these numbers because they're just some arbitrary center, because this is, you look, the true zero is where the peak of the Fraunhofer is. And we're going to have to track this true zero all the way, because that's how we know we have an average zero field flux within the Josephson junction. So we further crank the field 0 Tesla, 1 Tesla, 2 Tesla. Now we have a problem, because now we have no one lobe which is bigger than all the other lobes. All the lobes seem to be of a similar height. So this means something physically. It means that, well, it means that something changed in the current distribution. I'm going to talk more about it in a moment. So we map the critical current in a sort of 3D map. And if we can't track the zero, we're going to try tracking the side lobes and make sure that the measurement is kind of oriented so that we keep the center as the center. You see it kind of jiggles and wiggles. This is in-plane field. This is out-of-plane field. See, this is 3 milliteslas. This is 6 Tesla, so it's a factor of 1,000. And this took us a long time to do, because flux jumps and everything. But what we can see here are a few things. First of all, this is central lobe, and it disappears and reappears again. You have a side lobe and another side lobe. So we use the side lobe as sort of kind of yardstick that tells us that we have a fixed field. If we look at the critical current, we see that it suppresses and recovers again and suppresses again. Now this is very reminiscent of this data set taken again and again by groups studying ferromagnetic superconductors. And what basically is the physics behind the ferromagnetic superconductivity, ferromagnetic Josephson effect, is the following. You have Cooper pairs. You have a field which is in our case a Zeeman field and in their case an exchange field, which split the Cooper pairs. And that means that if you look at the Cooper pair, you're going to have an up and a down, which have a finite momentum. If you have a finite momentum, you have a finite wavelength. That means that your phase is going to flip somewhere along the way. Exchange biases are enormous, so this flip takes place in a few nanometers in ferromagnetic tunnel Josephsons, and that was done 20 years ago. What we see with junctions of hundreds of nanometers is that the Zeeman field causes the flip. Now, this physics is a bit hard to read, to repeat. We saw that vaguely in some other devices. What we know is that we have to be very, very cautious with other effects. If you reach 5, 6, 7 Tesla, it's very, very easy to introduce flux into your sample. Basically, any curvature, if you make the calculation, gives you a finite flux. So it's very, very easy you can have many, many problems, especially if graphene is on silicon and has some waviness. So what we did is build the graphene on HBN, and what you get is much cleaner graphene. And what happens now is that if you look at the graphene transport through such a junction, then you have something which looks like a Fabry-Perot interferometer. And this is a very paper by Moshe Ben Shalom, who was back then a postdoc with Andre Guy, on a graphene Josephson junction. You see these oscillations. These are Fabry-Perot oscillations of a resonator. And we see the same thing. And the reason we see these Fabry-Perot oscillations is that graphene under niobium selenide is very strongly p-type doped. And if you go to the N regime, you have p-n junctions on both sides. If you have p-n junctions, you have collimators. If you have collimators, you have a resonator. We have this resonator. And now we can start cranking the in-plane field, and we see that the resonator physics remains at 8 Tesla. So you have a very well-behaved ballistic resonator that remains a resonator with a suppressed supercurrent at 8 Tesla. And that, I think, is a very, very well-behaved Josephson device with extreme stability to in-plane field. Now we have a problem. Now we actually have to try to interpret the data. The problem is that if we look at the actual curve of why the suppression of about 2 orders of magnitude in the critical current, it doesn't make sense. It's not really clear what is the physics that leads this suppression. If you just look at numbers like the Tauless energy, and I'm going to go deeply because it's 501 now into this theory, but things simply don't work, and there's some physics at work here which we don't understand. So this is a bit of a technical compilation, so I'm gonna skip this, and I'm about 20 minutes in, right? Yeah. So I'm gonna skip this part of like a squid device that I had here, and go to the second part of my talk. In this particular data that I didn't show you, we see that the current redistributes. What the in-plane field does, it causes the current to redistribute to a narrow channel. We don't know why. Something to do with somewhere, maybe the edges are more immune to in-plane field. Maybe the electrons traverse the junction faster. We don't know. So this is the second part of my talk. How long do I have? So I can pace myself. 15 minutes? So 15 minutes, okay. So in 15 minutes, I'm going to tell you about a second project that was going on in my lab for the last year or so. In this project, we are trying to control Abrikosov vortices. So Alexei Abrikosov, Russian theorist, works in the 1950s in the Soviet Union, and he discovered the vortex lattice in 1953, but he doesn't publish because Landau didn't think it was a good idea. That's the Soviet Union, and you do what you're told. No, I don't know what was the relationship between him and Landau. That is from his Nobel lecture in 2004. After a while, Feynman publishes a paper about superfluid helium. Landau accepts, and then you have Abrikosov 1957, and he predicts the presence of vortices in type 2 superconductors. When were the vortices first discovered? That was 1967. This magnetic decoration by Eastman and Turnbull. Now, the fact that you have vortices already caused some stir. People had some nice ideas of what to do with them, because in the 1978 you have this paper by Hebard and Fiori from Bell Labs telling you that you could actually make vortex-based memories. Majorana is far, far into the future. These are classical magnetic field. There's a magnetic field flux, and these guys tell, look, we're going to thread them into a pinning site, and we're going to put a little Josephson junction here and a tunnel junction. We're going to detect them. That's very, very prescient. That's very nice. And that's almost 50 years ago, 45 years ago. Yeah? And basically, experimentally, what you have until the 2000s is not much. And then the scanning community gets into the game, and you have more and more groups that learn to move vortices around. So you have people moving vortices using STM, people moving vortices using lasers. My friend Ophir Ostlander, working with Katrin Moller, moved them using MFM. Bina using mechanical strain here in Bar Ilan, BIU. Yeah? So you have several techniques to drag vortices around. Now, why were people so interested in moving vortices around? Part of the reason, not only because people say there will be classical computers or quantum computers, they come from the prediction that vortices in Pli plus IP superconductors would be non-abelian. And if you manipulate non-abelian vortices, you have fault-tolerant topological quantum computation. You have this class of theory papers telling you that just stick the vortices in one place and move them around with some instrument, and you'll see miracles. Yeah? In Hebrew, you say ro'im yeshuot. You'll see great things are going to happen. Now, that's a problem, because what you need here, you need an on-chip method for moving vortices around, because you need this experiment to be done inside the dilution cryostat, which is very, very well filtered. You need to keep some of the vortices fixed while you move others. You can't just let things jumble around. And you need to be able to manipulate more than one vortex at a time. You need to be able to do these celebrated braiding operations. Okay, so now to do that, I need to cite Tolkien. Tolkien talked about rings, and rings hold all the power in the world. Tolkien tells you that 3 rings to the elven kings under the sky, and there are 7 and 9 and 1 to the Dark Lord. What the ring does, the ring rules them, finds them, brings them, and binds them. That's what a ring does. This is a winning of power. Now I heard that there's another Netflix series that shows you the power of rings. So we built rings. There's basically sort of ringy type of niobium devices that are about a micron in radius and have a very, very thin thread in the center. So you can drive current through these niobium sort of kind of micro loops. So we call them rings or loops. You take these rings and you etch them using either reactive ion etching or using FIB or using just lithography. You put an oxide, and then you put your favorite superconductor, which is in my case now selenide. And then you go to your local squid-on-tip lab, which happens to be my colleague Jonathan Anahori, who did his postdoc with Eli Zeldov, has a scanning squid-on-tip lab, which is functioning and operational. So this is a squid-on-tip, which scans what happens underneath, and that's the device I showed you before. So this is you have rings, a superconductor, and a squid that's all packaged together. You cool that down to about 240. What you have now, so you cool that down at the finite field. You have these little vortices all here. This is 1 micron. These shades are the rings. Now, to see the statistics of these devices, we cool them down many times, about 600, 800, 700 measurements, when integrating about 5,000 vortices, and we see the following pattern. First of all, the vortices tend to move away to shun the actual ring, and you can understand that because it's niobium. Niobium has a much greater stiffness than niobium selenide. Then you have, it repels magnetic fields much more effectively. The vortices tend to localize very, very precisely at the center of the rings. The statistics is better than 100 nanometer precision. And the fact that Yoni has this resolution to see that is also pretty remarkable. So you can actually know that you localize the vortex at a very, very well-defined precision. And now the question is how effectively you can move them around. And there's something we did which was correct without knowing that we did the correct thing. We designed this slit in the ring, which is kind of linear and imposes a force vector which pushes or pulls a vortex, depending on the polarity, in a given direction. And that's very useful because it means that we have something that looks like the symbol of Mercedes of we can pull and push from this central region. And if we have this vortex here now, and we apply what we call the push operation, meaning that we're increasing the current until bloop, the vortex disappears. We look for it, we find it here. This is another vortex which is kind of looking around. It's not participating. It's sort of an observer. Hello? Yeah. So now, so that was the push operation. We also have a pull operation. We reverse the polarity. We look at the vortex. We pulse and pulse and pulse, increasing the current until it dislodges and goes back right to the center of the vortex, of the loop. So we pulled it back to 100 nanometer well-defined location. So now the next thing we can do is try to shuttle the vortices. So now we cooled down, we tried several cool downs until we had only 2 vortices around the device. That's one centered around loop, which we call this loop, which we call number 1, and one just kind of lying in the middle. So we initialize the system by creating a pull operation into loop 3, and we have the vortex A. Now we call this vortex A. This is called vortex B, and this is the initial position. We have 1 in one loop and 1 in the other loop, and this is just looking around. This is just not going to do anything here. It's going to be jumping. So now we exert a push operation of vortex A, and it just jumps to somewhere in the center, and we exert a pull operation by this loop, which is loop 2. So vortex A was now moved to the center and was shuttled from loop 1 to loop 2. So we had this situation. We started from here. This moved here. And now we can repeat this time and again, and we want to try to move these vortices around, and this is what we get. And this is the braiding operation. Now, this is the braiding operation. I dare say that's the first braiding operation. See? And that took about a whole weekend. But it can be done much, much faster because you need to be able, just being able to sense where the vortex is, you just need a local center which operates fast. We didn't try to do that. The squid is, it works in DC. But, so, just stop that just to not to blind you. Kind of get you start braiding and you start like your dog, we're running around in circles. So, don't want that. But, we're very, very happy with this results, and I think we have kind of probably have running very close to 5 more minutes. Good. So that's so I'm going actually brings me to the summary. So we have a few minutes to talk. So niobium selenide here, I think it's 20-30 nanometers. It's pretty kind of standard thin bulk. The niobium is 100. So one of the things we learned was that the loop has to be thicker than the superconductor to be able to create this very strong pinning effect, because you need to be able to kind of exert the pinning potential on the superconductor. And then the other superconductor actually does that even without running any current, just by being there. So the entire vortex line is moving, or it's a big vortex? Or? Oh, no, that's an entire vortex line. So that's, okay, so the vortex line actually threads the whole thing. It threads the whole device. Otherwise, it wouldn't shun the niobium. It's actually kind of a vertical line that's threading the whole thing. It's not a pancake vortex, nothing. These are kind of type 2 BCS layered.
If it cannot go through the niobium, right, from the center to the edge, how does the line cross it?
So it can probably do that for a very short time. So yeah, it's a good question, but there's probably, look, it's a potential barrier. So if it's a potential barrier, if you give it enough force, if you pull it, you kind of pull it above the potential barrier. It's actually a good point because that means you can now engineer this potential barrier. So one thing we're doing is we're thinking of creating like threads, like sort of creating these channels that will allow to move the vortices by favoring certain channels, because the thickness of the ring actually imposes the pinning potential. You can engineer the pinning potential by the superconductor which is underneath. And that's kind of something that we learned just after doing that. It's kind of part of the intuition which we had to put into words after we saw the results. So what we learned from this experiment is that niobium rings allow you to do on-chip control of vortex position. And they can be shuttled and braided. And now there are several questions. If you look deeply into the Majorana literature, there's one word that keeps coming back and back. The process has to be adiabatic. Now, what I did now is I showed you that there's an object, and Shachal used the term running with a cup of coffee. Yeah? You have the vortex, and you basically, it's like giving you a cup of coffee by throwing the cup of coffee. So I don't know if I send the cup of coffee gliding perfectly on a very even surface, but basically the idea is the coffee doesn't spill. And we don't know if coffee, meaning quantum coherent information, spills or not. So the question here for the theorist is, how can we measure if the quantum information in the vortex is contained? If you're just kicking, you basically kick a ball and hope that the ball doesn't break. And the second question is, how can you design what is this kind of vortex choreography? Because again, you go look into the literature, they tell you that you need to have 4 vortices and you have to bring them together, pull them apart, run around. It's like these medieval dances with people dancing around a big pole with wires. It's called a maypole. So well, you have tons of literature telling you to do just that. But I think now we're providing an experimental input that says, this is how these braiding devices are going to work. Well, that's one way they can work. And now let's see what's the realistic constraints on the design. Yeah.
You talk about the adiabaticity for that process, but if that braiding is about the topological computation, why is adiabatic? So
according to everything that the theory tells you is that the non-abelian particle has to move in space adiabatically. Why it should be adiabatic, I can only guess, but that's sort of, for me, it's given by theory. What do you say?
Because you interpret healing.
Okay, yeah.
Because the more practice better.
Yeah. So again, to be honest, these vortices move pretty fast. They move, the velocity of a vortex is several kilometers per second. And then the question is, what does it mean that they move kilometers per second?
It has to be, it has to be faster than the gap.
Yeah.
Maybe if you go very, very, very fast,
Yeah.
then it might be excited, not the gap
Right.
at all.
Yeah. But then the question is, what excites the gap? What excites the gap? Which is the gap?
There's a gap.
Yeah, there's a gap.
You have to go to the gap. You go to the quantum
No, you're right.
ground state, then you have a gap, right?
Right. But
That's if you get the ground state.
but what do you compare to the gap, Moti?
Okay, if you go very, 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 very fast, you have a certain potential.
Yeah. No, so the question is, but I think you're right, you're asking the right question.
I'm talking and you talk at the same time.
Yeah, that's always what I do, I'm sorry.
So I'm saying if you go very, very fast,
So-
what's the global measurement that you can do that I will see, oh, the wave function now is different.
Okay, so that's a question that, the same question that you asked me, I went to 20 meters from your office to Adi, and 50 meters, yeah. But I went adiabatically, so I didn't go very fast. And what he told me, so I'm going to repeat what Adi told me. So the question is the following question. Yes, it's great that I can move vortices, but this is basically almost a classical measurement. It's not a quantum mechanical measurement. What is the measurement that tests non-abelian properties? And what Adi Stern tells me is that the following thing. It's like a recipe from a quantum mechanical cookbook. Take 4 vortices, topological. Bring 2 together, make sure that they entangle. Remove them. Now, rotate them and bring them together again. And now what's going to happen is that If you are in a sort of state 1, then there'll be an excited state which either going to be manifest as a charge or in a populated state which you should be able to measure through some, some kind of a microwave excitation. I don't know, I'm not telling you how I'm going to measure that, I'm telling you what theoretically is supposed to be an observable. And of course, it'll either be there or not. Now, I'm not saying how to do that. What I'm saying is that if you look at the body of literature that tells you we're going to do braiding, which you probably saw 1,000 papers doing that, they're very vague on how it's going to be done and what's going to be the result. And I think if you look at what's going to be the result, it's actually very, very challenging to measure a topological yes-no property. But I think it's the question that has to be asked. And with respect to what you said, your comment before is that you said, okay, there's a velocity. But what I'm asking is, I'm not asking you, I'm asking everybody. There is a velocity. What is the energy? So there's a gap, but I have to compare it to some other energies. What is the energy? So something has to couple to the vortex and create this excitation energy. What is it? What is it? What is the system that I have to solve that excites the vortex because it moves? So somehow the fact that the vortex moves causes dissipation, and we know that. It can cause excitations, and we know that too. But we have to come up with something quantitative measurable that actually creates this excitation where to the first Caroli de Jeon state or... Yeah. Yeah. No, I agree with you. Yeah, but I think there is a sort of an open question of what causes the vortex excitation here, in the definition of adiabaticity. Yeah, and sort of answer your question with a question. Yeah, I'm probably out of time, right? So.
You have 5 minutes.
I have 5 minutes. Okay, so the more questions will be.
I have a question.
Yeah.
So for example, can you you can manipulate. First of all, I'd like to. How do you push these vortices to another place? Mm-hmm. You apply the voltage first. So the way it's done is in the following way. It's actually very, very simple. Where do I have it here? We drive a current. Mm-hmm. So we drive a current either in a positive or negative orientation, polarization. Now, there is a positive polarization would be an attractive force, a negative polarization would be a repulsive force. Now, what's really important is that this is not a circle. If it were a circle, there would be no force. There'll be just a minimal energy, and that would not move. The fact that it's sort of kind of a U-shape, sort of a horseshoe, breaks symmetry and creates a vector. And this magnet sort of, you can calculate just by integrating the biggest of Hadar's law, the magnet, it's just classical electrodynamic, electrostatics, magnetostatics, either pushes the vortex in this vector or pulls it with kind of, there's like in kind of, there's an angular a range that from which to which it pushes and from which it pulls. I understand. Then how do you stop vortices when you applied current? Then vortices start to move and need to stop somewhere around. Can you control that part? Again, how do you stop? How do you stop? Okay, so the way we work is if there is no pinning, it keep going and. Well, so why the reason? Again, this is something that apparently this design gives us for free. There's a minimal potential here. There's the minimum pinning potential around here. So globally, if we kick the vortex, basically what we do is we increase the power, and it kind of starts rolling like sort of a golf ball, and just going to stop at a valley. The valley happens to be here, and it happens to be stopped here. Kind of, if you roll a soccer ball, it's going to stop every time in a different place, but it generally tends to stop here. So what we do is kind of we increase the current, while looking locally with the squid with the tip at the position of the vortex until it disappears. And then once it disappears, we basically go looking for it. It's like you have your eyes closed, you look at the ball, you kick the ball until the ball disappears, and then you open your eyes and go looking for the ball. My comment is like this. If you want to do braiding experiment, then you need a vortex, anti-vortex. So you braid first, then you need to analyze them. To see the electrons pops up or not, to prove the non-abelian statics, something like that. But in your system, you can manipulate, but probably it's very hard to analyze them in your configuration. How do you analyze two vortices between vortex and anti-vortex? how do you analyze it using your system?
So basically, it's the same answer that I gave when Moti's question before. The simple answer is that I don't know, but the more educated answer is I went to speak to theorists, and they told me, basically they referred me to the body of literature that exists. By the way, the fact what you're saying with vortex, anti-vortex, that's, I didn't hear, that's something that they didn't tell me, that there has to be anti-vortices. It makes life harder, but not impossible, because these are all vortices of the same orientation. You can see anti-vortices, they just don't look like a bright spot, they look like a dark spot. So vortices, anti-vortex has an opposite polarity.
It's opposite, so it's moving in opposite way, so you never analyze them in your configuration. That's what I'm worrying about.
Here we are not looking at because there are two vortices of the same orientation, so you can't annihilate them. So you may be able to bring them close, but you can't annihilate them.
If you have same polarity of vortices, you never get prove the non-abelian statics. You need a vortex and anti-vortex. So that make them annihilate, then electron pops up due to the non-abelian statistics. You detect kinds of electrons by 50%.
So
that's
I can stand here and wave my hands and tell you how I'm going to do this experiment. I think it'll be more productive if we sit and talk about it. And I think that the chairman is signaling to me that I have to leave the podium and clear the stage for the next. Maybe.
Can I ask? I would like. I would like to ask about the first part. You said the magnetic field is in the plane, and I wanted to know which direction in the plane.
So the magnetic field can be in. Typically, we design these Josephson junctions that are either parallel to the crack or perpendicular to the crack. We don't have the ability to rotate it.
No, what I'm saying, if you have the Josephson current, if it goes this way,
it can be either. We actually measure both. Usually, each and every device we cool twice. We cool it. We measure in one orientation, we rotate it by 90 degrees and we measure it again. So basically, the answer is both.
Thank you.
Yeah.
Okay, I'd like to stop here and thank the
you.
speaker again.